folks. Welcome to
Vector calculus.
Alright folks, welcome to the next lecture in vector calculus. Today we're going to be talking about direction cosines, which tell us how far an angle is, or a vector is, from each one of the three axes. The x-axis, the y-axis, and the z-axis. Let's go ahead and check it out with a nice example. So here I have my x, my y, and my z-axis, right? So traditionally I'll just label it x, y, and z. And let's say I have some kind of a vector. Let me use the green color, and I'm just going to draw a random vector out here in 3D space. So here I've got a vector. Now this vector obviously makes some angles, right? It makes some kind of an angle with the x-axis, some angle with the y-axis, and some angle with the z-axis. And as a matter of fact, I'm going to color code all of these three angles. These three angles are each given a letter. So the angle that our vector makes with the x-axis, we like to call it alpha, okay? The angle that our vector makes with the y-axis, let's call it, well, as you expected, beta. And the angle that our vector makes with the z-axis, let's call it gamma for the time being. So here's gamma. And now what we want to do is just find out what these three angles are. How can we do that? Well, it turns out it's not too bad. Well, let's say our vector has some components. Let's give it some numbers. Let's say our vector is some vector, I don't know, 1, 3, 6. Okay, that's our vector. Now, to find the angle that our vector makes with the x, y, and z axes, what I have to do is use the second definition of the dot product. The definition that tells me what the cosine of these angles are. So let's start with the cosine of alpha. So cosine of alpha is going to be what? Well, notice that I can take the dot product of our vector. Let's call our vector v for the time being. I can take the dot product of our vector v and the unit vector in the x direction, which we call I hat. So if I take the dot product of my vector v with I hat divided by the magnitude of my vector v and the magnitude of I hat, that's going to give me cosine of alpha, right? And hopefully you know how to simplify this, right? The magnitude of I hat is just 1, so you can make life easier for you in that way. We're gonna do the same thing for cosine of beta, right? Cosine of beta, right? What's that gonna be? Well, once again, we're gonna take the dot product of our vector v, but this time with the unit vector in the y direction, which of course we like to call j hat. So if we take the dot product of our vector v with the j hat, and I divide it by the magnitude of my vector v times the magnitude of j hat, that's gonna give me cosine of my angle beta. And of course, finally, I can do the same thing for gamma, as you might imagine. I'm going to take the dot product of what? My goal is to find cosine of this angle gamma. To do so, what I have to do is find the dot product of my vector v with this unit vector in the z direction. And what's the unit vector in the z direction going to be? Well, it's going to be k hat. K for kite or kangaroo. So I'm going to have v dot k hat all over the magnitude of my vector v times the magnitude of k hat, which of course is a unit vector. And now you can go ahead and plug and chug in the numbers, right? What is cosine of alpha going to equal? Well, if you take the dot product of our vector v and I hat, what's that going to look like? Well, do that. 1, 3, 6 dot, what's I hat going to be? Well, it's going to be 1, 0, 0. Right? That's the unit vector in the x direction. That's why all the other components are 0, and only x has the unit of 1, because a unit vector in the x direction is going to have a magnitude of 1. Okay? And what's the magnitude of our vector? Well, you can go ahead and use the Pythagorean theorem. It's going to be 1 squared plus 3 squared plus 6 squared, and square root that. And the magnitude of the unit vector is just 1, so that's a no-brainer. Right? So whoops, don't mistake that with the dot product. So let me put a time sign. So what am I going to be left with in the numerator? Well, as you can observe, hopefully, as you can hopefully see, I'm going to be left over with just the x component of my vector. So this is just going to be 1 on the top divided by, what is that? 1 plus 9 plus 36 That's going to give me square root of 46. And that means my angle alpha is going to be arc cosine of 1 over square root of 46. Let's try to employ the same methodology for cosine of beta, right? What are we going to do here? Well, same course of action here, right? We're going to take the dot product of our vector with the unit vector in the j direction, in the y direction, which is j hat. So what am I going to have? Well, what's my vector? My vector is 1, 3, 6. What's j hat? Well, this time it's going to have a component of 1 in the y direction and a component of 0 in the x and z direction, and divide all of that by the magnitude of my vector u, or v. So 1 squared plus 3 squared plus 6 squared. And the magnitude of a unit vector, of course, is just 1. So try to keep that in mind. So what are we going to be left with for our numerator dot product? Well, we're just going to have 3 on the numerator, as you can see, divided by the square root of 46. Once again, it's going to be the same denominator. And so what is our angle beta going to be? Well, come over to this side, and if you take the arc cosine of both sides, you'll be left over with beta being 1 over, or rather 3 over the square root of 46. And you can go ahead, plug that in your calculator to see what that's going to be. And finally, we come over here, right, with gamma. How do we find the angle gamma? Well, once again, do the same thing, right? You're going to have on the top, what are we going to have? Well, hopefully I don't run out of ink here. That'll be live embarrassment. But what's my vector v? It's going to be 1, 3, 6. Dot, what's my vector k hat? Well, my z component is going to be 1, but my other two components will just be 0. Divide all of that by the magnitude of my vector v, and that's just going to be square root of 1 squared plus 3 squared plus 6 squared times the magnitude of k hat, which is just going to be 1, right? And so what am I left with on the top here? On the top, I'm just left over with 6, right? Just my z component. If you do 1 times 0, that's 0. 3 times 0, that's 0. 6 times 1, that's 6. Add them up, you'll just get 6 on the top, square root of 46 on the bottom, and that means our angle gamma, which we've been trying to look for so long, is going to equal arc cosine of 6 over square root of 46. Okay, and that's that. But one more thing before we leave it off on this note. Notice. There's a wonderful property here to be observed. Wonderful property here to be observed. And that is that the square of the sums of the direction cosines equals a magical number. No matter what the vector is, the square of the sums of the direction cosines will always be a magical number, and that number is 1. And I'm going to prove that right now. We're going to prove that right here, right now. So here we go. Let me erase all of this work. We don't need that anymore. Hopefully you copied it down, or you took a picture, whatever you need to do. So now let's go ahead and these were the answers for the previous problem. Now what we're going to do is actually prove this amazing property of the direction cosines. And that property tells us a very simple fact. It tells us that if I take cosine of alpha, square it. If I take cosine of beta, and square that. And finally, you guessed it, if I take cosine of gamma, and I square that, and I add these 3 guys up, I'm going to add 3 of these fellows up, what I'm going to be left over with is just 1. And how do we prove that? Well, let's go ahead and do the math. What's cosine of alpha? Well, cosine of alpha, as you can see over there, is just my vector v dot I hat over the magnitude of my vector v, right? Because of course this over here is just 1. And I'm going to square that. Plus my cosine of b is my vector v dot j hat over the magnitude of my vector v. Square that. Likewise, the cosine of gamma is going to be v, my vector v dot the unit vector in the z direction, k hat, divided by the magnitude of my vector v. Square that. And now what am I going to have? Well, I'm trying to prove this as a matter of fact, so let's actually go ahead and write this down so we don't mistake it for anything. So let's erase that. So we're trying to prove that this is equal to 1. Prove. Okay. Now, what do we have over here? Well, v dot I hat squared. Well, that's pretty perplexing if you ask me, but we're going to keep that on the numerator. But what do we have on the denominator? What do we have on our denominator? Well, observe that in the denominator, we're going to just end up with the magnitude of our vector v squared. Likewise, for this one, we're going to have our vector v dot j hat, square that, divided by the magnitude of our vector v squared. Finally, for our last term, we're going to have v dot k hat, square that, divided by the magnitude of our vector v squared. And it's worth putting the vector sign on our vector v. Why not? Some people will protest because of that. I don't think that's worth protesting over, but okay. And now we can just add up these numerators just like regular fractions. So what are we going to be left over with here? V dot I hat, well, that's just going to give me the component of our vector in the x direction. So we're going to have vx squared. Likewise, we'll be left over with the component of our vector in the y direction. If you don't understand why, just rewind and watch carefully. You'll see we only end up with the x and y and 3 components. And likewise, for our last term, we're going to end up only with the z component of our vector and square that. And divide all of this by the magnitude of our vector squared. And now notice, what do you have here? Well, the magnitude of your vector squared is going to be what? How do you find the magnitude of a vector? Well, remember, to find the magnitude of a vector, we'll be using Pythagorean theorem, right? So you'll just have what? What are you going to have? Square root of vx squared plus vy squared plus vz squared. But we're squaring the magnitude, right? We're squaring this magnitude, right? So if you square the magnitude, it's going to cancel out. This square and this square root are going to cancel out like that. Easy as pie. And so you're left with what? On the numerator, you're left with vx squared plus vy squared plus vz squared. All this messy jumble of mess. And on the bottom, you're left over with vx squared plus vy squared plus vz squared. But notice, the numerator and denominator are the same. And so, boom, you're left over with nothing but 1. And so thus we've just proved that the sum of the direction cosines are indeed 1. And that's it for this lecture on vector calculus, and we'll check you out next time.
Embedded plus MKO plus scaffolding equals learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO, and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.